So in our last video, we looked at limits at infinity for polynomial functions and rational functions, and we found that those worked really nicely. Pretty much exactly the way that we've always thought they did with end behavior. We just have to look at the largest degree terms, right? So what we're going to do is keep this line of thinking going, but we're going to look at a weird example that it's not quite a rational function. It's really close. And the little subnote here is that really this is a lesson about square roots and signs of those things. So keep that in the back of your mind, and when you see something happen, you can say like, oh yeah, I discovered this, and then I'll show you what's going on. Then we're going to do a little revisit to the squeeze theorem, and we'll use the squeeze theorem to talk about end behavior, and then we're going to take a look at a new class of functions, hyperbolic trig functions. Whoa! What are those? You'll see. They're not that big. All right, so let's get this thing started off with a weird example. We're going to consider this function. It is not quite rational, but it's close. We're going to determine the end behavior. What I mean by this, when I say not quite rational, is that we do have a polynomial on the top, and we have a polynomial on the bottom, but we have really the square root of a polynomial. And that square root is throwing off the rationalness of this function, because we don't actually have just a polynomial. Now, it's possible that this thing is a perfect square underneath, so we could do some factoring and cancel out the square root or whatever. I don't know. We're not going to do that, though. What we're going to do is find the end behavior. So that means we're looking at limits at infinity. So let's start with the limit as x approaches positive infinity. These first couple of steps hopefully feel pretty good to see. We're going to look at the limit as x approaches infinity of this whole function, and then we'll go ahead and say the limit of a quotient is the quotient of the limits. So we'll put that limit in the numerator and denominator. And look at that numerator. Isn't it just set up perfectly? Polynomial function. Biggest term is the only one that matters, right? That's great. I'm not going to do anything with this yet because I got to deal with this denominator. You might also remember that we have this property with roots of functions that says if you've got a square root, you can put the limit underneath as long as you don't divide by 0. You'll notice that this is conveniently set up to guarantee that we don't divide by 0. We have only even exponents, meaning all the terms are positive, right? Even if you put negative numbers in, we raise them to even exponents and they become positive, and we're adding things. So this is at worst 0 plus 1, and at best it's a positive number plus a positive number plus 1. So we're going to have square roots of 1 or higher, meaning we don't have to worry about non-real numbers when we bring this limit underneath our square root. So I'm going to leave the numerator the same for now, bring the limit under the square root, and now you'll notice, whoa, look at this! Polynomial function on top. We'll just grab that 8x cubed. And now we're looking at the limit of the polynomial function on the bottom under the square root. So we'll just grab that 4x to the 6. Look at this. This is great. Okay, so now what we can do is start bringing our limits back. We bring our limit out of the square root. We bring our limits back in front of the fraction. And you'll notice, wait a second, I just turned the square root of 4x to the 6 into 2x cubed. That should make some sense, right? The square root of 4x to the 6th is 2x cubed, right? Square root of 4 is 2. Square root of x to the 6 is x cubed. Good to go. And now, oh, isn't this convenient? We have this ratio of things that reduces down to the constant 4. So we have this limit is 4. And so what we could say is as x goes to infinity, there's a horizontal asymptote. At y equals 4. That's what we've really found. Remember, if we said that this limit exists, that means there's a horizontal asymptote at whatever that y value is. Great. Let's do the other side. Now, we're used to functions having the same horizontal asymptote on both sides, right? And if we look at the work that we've done here, much of it we can recreate. So we're going to recreate it. So we'll start with the same thing, but we're going to look at the limit as x goes to negative infinity. And we're still going to look at the limit on the top and the bottom. There's nothing new there. We still have a polynomial on the top, meaning we can still just look at that biggest term. We kind of have a polynomial on the bottom. We got to put that limit under the square root. And maybe this negative infinity is throwing us off a second because like, whoa, wait a second. Negatives under square roots. That's bad. But remember, all of these terms are going to be positive. So if we chuck it under there, we're going to have even exponents on everything. That gets rid of those negative signs, so we have no problems there. Things are looking great, right? And now, again, polynomial function, only the biggest terms matter. Wait a second, we can start backing this limit out again. And wow, this limit is 4. I'm going to sit here for a second and see if we can find the problem. Remember what I said earlier. This example is all about square roots and sines, meaning let's focus on this. We looked at a limit as x approached negative infinity of this square root, and we're left with 2x cubed. The problem is that the square root of 4x to the 6 is not actually 2x cubed. And you might be looking at the screen going like, wait a second. Yes, it is. The square root of 4 is 2. The square root of x to the 6 is x cubed. But that's not actually true. In fact, the square root of x squared is not x. And that's really what this boils down to. Let's think about sines with square roots. Let me just pick a clear-cut example here. Let's set x equal to negative 3. We can see what's happening here. Is the square root of negative 3 squared equal to negative 3? Of course not. Negative 3 squared is 9, and we can see that the square root of 9 is clearly not equal to negative 3. It's equal to 3. So what we need to do is say, yeah, these are related to each other, but they're not necessarily equal. The square root of x squared is equal to the positive version of x, the absolute value of x. Now, in our first limit that we did, this didn't really matter. But what we're going to do is we're going to say, in that first limit, as x is going to infinity now, see, we're back to the very beginning example, this square root is actually going to be equal to the absolute value of 2x cubed. Now, that doesn't matter. You might remember that the absolute value of x is a piecewise defined function. It's negative x if x is greater than 0, and it's x if x is, if x is less than 0. There we go. And it's x if x is greater than or equal to 0. X is going to infinity. This stuff is going to be positive. The absolute value doesn't do anything for positive stuff. So we can say the absolute value of 2x cubed is equal to negative 2x cubed if x is less than 0, and positive 2x cubed if x is greater than or equal to 0. And if x is going to infinity, it's greater than or equal to 0, so we can just swap it out with regular 2x cubed. We didn't run into any problems. But now, what we're going to notice, I'm going to grab this and bring this to my next slide. What we're going to notice is that if we still have this piecewise defined absolute value function, now when x goes to negative infinity, the stuff on the inside is actually negative, right? When you cube x, that's going to preserve the sign. If x is negative, then x cubed is negative, and so 2x cubed is negative, and this absolute value would change things. So what we need to do is flip the sign of this. It looks like I'm making this negative, but what I'm actually doing is making it positive. Oh no, there's a limit here that didn't get changed. That is supposed to be x going to negative infinity. Because if x is going to negative infinity here, then that means that x cubed is negative, and so when we put another negative out front, that makes it positive. That's kind of weird, right? So now we have a negative over a positive. This turns into negative 4. So we have a horizontal asymptote at negative 4, and this is as x goes to negative infinity. So that's kind of weird. So if we were to graph this, let me just sketch this really quickly. Our asymptotes look like this. On one side, we have a horizontal asymptote way up here. And on the other side, we have an asymptote way down here. And our function does a bunch of stuff in between, la-di-da-di-da, but it gets up to positive 4 here and down to negative 4 here. There are tons of functions that do things like this. Our inverse tangent function has different asymptotic behavior on either side, right? But now this function does too. And it's because of that square root. So just keep in mind that we're really actually looking at an absolute value of things when you deal with this square root here. And so we have to change the sign appropriately. Here's another weird example, one where we're going to be using the squeeze theorem instead. So we'll remember the squeeze theorem. This is one where we have to bound our function above and below. And so here we're going to find the end behavior of this function, meaning we're going to find a limit as x goes to, we'll start with infinity, of sine squared 3x over 5 plus x. What we need to do is to come up with some bounds. So we have to say, maybe I'll write this over here. We have to say that sine squared of 3x over 5 plus x is bounded above by something and bounded below by something. Some functions. And remember, we're going to look at the limit as x goes to infinity of all these functions, and if these two are equal to each other, that means the one in the middle has to be as well. So we'll start with our sine function. We'll say sine of 3x, maybe I'll put this in a different color. Sine of 3x is bounded by 1 and negative 1. Now what happens when we square things? Well, all the negatives are going to turn positive, and so that means actually our smallest value for sine squared of 3x is 0. And this is true for all x values. What we need to do now is to get this denominator on here. Now notice we want our denominator to be positive, so when we divide we don't switch the signs of the inequalities or the direction of the inequalities. X is going to infinity, so that means that 5 plus x is positive. So what we're going to do is divide by 5 plus x. And this is going to be true for x greater than 0, right? All the positive ones. And actually what I should do is say not greater than 0, greater than negative 5, really, right? If x was negative 4, 5 plus x is still positive. So for all the big x values, this is true. For anything smaller than negative 5, we'll just flip the order, and I'll show you that in a second. Okay. So now what we can do is say, well, this left side is still 0. And then we have sine squared of 3x over 5 plus x less than or equal to 1 over 5 plus x. And if that's true for all of these x values, then it's certainly going to be true for all the really big x values. So I'll just toss this limit statement on here. This limit on the very far left of the R inequality is easy. It's 0. This limit in the middle is the one that we want to know about. And this last limit is hopefully one that we can see. We have a power function on the bottom, right? A polynomial really on the bottom. You could put the limit on the bottom, and then this is really the same thing as the limit as x goes to infinity of just 1 over x, right? That's what we found with those rational functions. And so we could say, oh, wait, this is really going to be 0. So now our limit that we care about is stuck between 0 and 0. That means it has to be 0. Cool. Let's find the other end behavior. We're going to do the exact same thing, except now, since we're looking for the limit as x approaches negative infinity, we'll be looking at small x values, or maybe I'll say really big but negative x values. So we'll start with the same sort of bounds that we had earlier. We'll say sine squared of 3x is still between 0 and 1. Again, because we're squaring it, it normally would be between negative 1 and 1, but squaring it gets rid of the negative stuff, so our smallest possible value is 0. Now we'll divide by 5 plus x, but since x is going to be really, really negative, we're going to flip our inequalities around. So see how I'm changing the direction of my inequalities here? And this is for the x values that are less than negative 5, which we're looking at because x is going to go to negative infinity. So suddenly, we can toss some limit statements on here. If that's going to be true for anything less than negative 5, then it's certainly going to be true for all the really, really negative x values, like the ones that are getting sufficiently close to negative infinity. That doesn't really make sense. The ones that are getting really, really negative and large in magnitude. I think that's how we said it in our definition earlier. But what we'll notice is that the two limits on the outside are still pretty easy to deal with. And so now, sure, our inequality is the opposite way, but it doesn't really matter because this limit is still bounded between 0 and 0. So hopefully we can see by the squeeze theorem that this limit is also 0. Great. So we can still use the squeeze theorem for these limits as x approaches positive infinity or negative infinity. We just have to be careful about when we're doing multiplication and division to make sure that if you do multiply or divide by a negative, switch the direction of your inequality. All right, lastly, let's talk about hyperbolic trig functions. These are probably brand new to you. Most students that I get in Calc 1 haven't seen hyperbolic trig functions before. Maybe you have, though, but these are what they are. We'll go into more detail about what these hyperbolic trig functions actually are doing later on. I'd like to talk about them a little bit in Calc 2 when we talk about conic sections with hyperbolas and stuff like that. So if you want to, you can try and find, I might have a video about that somewhere on YouTube. So you can go and see if you want to find that. But what we're going to do is for now, just state the definitions of these. Hyperbolic sine, or sometimes people will call this sinh, is defined as the exponential e to the x minus e to the negative x over 2. And hyperbolic cosine, or sometimes people will read this as cosh, is e to the x plus e to the negative x over 2. Notice we just are switching this sign right here. Since this is just combinations of e to the x's and stuff like that, we can find end behavior limits. So let's just deal with hyperbolic sine for now. And let's take a look at the limit as x approaches infinity of e to the x minus e to the negative x over 2. Maybe I'll split this fraction up, and I'll just write it as e to the x over 2 minus e to the negative x over 2. Then what you could notice is that we can factor out a half. I could have done that earlier as well. Maybe I'll write it like this. And we have e to the x minus a half times the limit as x goes to infinity of e to the negative x. And you might remember these end behavior limits from when we talked about transcendental functions earlier. If not, no big deal. Let me draw the graphs for you. We're looking at this exponential function, e to the x. As x goes to infinity, it's pretty clear that this thing is going to go to infinity. And for our negative exponential, our flipped exponential, as x goes to infinity, this thing goes to 0. So we have infinity minus 0. So hopefully you can see pretty clearly that the end behavior on this hyperbolic sine function is infinity. Let's take a look at the other side. We'll do the exact same thing, but now we'll approach negative infinity. So now we've got half times our limit as x goes to negative infinity of e to the x minus half times our limit as x goes to negative infinity of e to the negative x. And now we can just look at these ones, right? This x going to negative infinity on our blue regular exponential function, that's 0. And this one for x going to negative infinity on e to the negative x, that's infinity. So we have 0 minus infinity, which is going to be negative infinity. So there's our end behavior. Our end behavior for this hyperbolic sine function looks like this. It's got some cool stuff going on in the middle, but that's the end behavior of it. I'm going to encourage you to go ahead and do the same thing for the hyperbolic cosine function. You'll notice that there's really no difference other than the positive sign in between, right? Instead of subtracting those things, we're adding them. You could think about how to define hyperbolic tangent. Well, if regular tangent of theta is sine theta over cosine theta, then maybe hyperbolic tangent of x is hyperbolic sine of x over hyperbolic cosine of x. You'd be right. We'll mess around with these hyperbolic trig functions every now and then in this class just to give us some kind of cool little examples to look at. But hopefully that's helpful to really finish up our ideas of limits at infinity.